Hello everyone. It's an honor for me and Yunming to present our work unlocking ECMP programmability for precise traffic control. This work is together with my colleagues in Tencent and the University of Michigan, Tsinghua University, and Northwestern University. I will present the first two parts, and Yunming will present the next two parts. Firstly, let's talk about the randomness. It's vital in today's network as it exists in many network functions. A key example we say is that the equal cost multipath routing, or ECMP routing. ECMP enables many benefits such as performance, it allows load balancing and fault tolerance, as it realizes through extra redundancy. Let's show the illustration of a simple topology. There are two paths. Let's say that a packet are sent from the servers on the left. At the left switch, all the packets will go through the ECMP process. Specifically, some of their headers will be input to a hash function, and the hash output will be used for the mapping stage. Here's the output part will be port will be selected, and then the packet will be assigned to either passes. Ideally, each pass has the same load. ECMP is very efficient and easy to implement, so all switch we know of support ECMP, and data center network today are built upon the ECMP. Here the figures show that in a typical network topology, there are multiple equal cost paths between any pair of the servers. However, randomness, we know that it is not perfect. It also brings some problems. It does work for all scenarios, but in some critical scenarios, we need the precise traffic control. For example, network failure by reparsing flows. Let's go back to the simple topology again. And let's say that a flow is mapped to the upper path. Everything works well until a failure occurs in the at this path. This can be any failures, such as switch failures, path failures, or misconfigurations. To solve this problem, we can reparse the flow. For example, we create a new flow or modify the header fields of the old flow. For example, we can retry the ECMP and hope it selects different passes. And because the ECMP is uniformly random, the chance of selecting either path is 1/2. So the chance of the success rate is 15%. When it fails, we can retry, and for each trial, the success chance is listed here. Eventually, we will succeed. We know that for 3 trials, the success rate is only 90%. Besides network failures, there are many other scenarios that requires precise traffic control, such as load balancing, network failure localization, multi-flow application, and more. An ideal world is that we could have both randomness and precise traffic control coexist. So we want both random and law and order, but this is not easy for 2 reasons. One, as I mentioned earlier, there are a lot of precise traffic control scenarios, and we hope that we can support all of them at the same time. Next, there are also compatibility issues. We hope our solutions can be deployable in the today's data center network, meaning that it needs to be supported by all the existing hardware. Okay, how can we do that? Given the ECMP is widely supported today, and it's where the randomness is enabled. We are thinking, can we modify ECMP to realize precise traffic control at the same time? To answer it, let's look at the ECMP closely. First of all, the packet headers will be used as the input to a hash function. So the first solution is, let's update the header fields to change the hash outcome. But this doesn't work because we don't know how the modification will change the outcome unless we exactly know the hash function. In fact, a previous work has done this and found that it's possible to leverage the linearity in hash algorithm. However, the downside is it requires knowing the hash algorithm and parameter in advance, and also the proposal does not work in heterogeneous environment. Where there are different kinds of hash algorithm used by different types of switches. Okay, let's move on to the next stage. Can we modify the hash algorithm itself to produce different outcomes? Unfortunately, the answer is no. So randomness still exists. We cannot easily find two hash algorithms that always produce different outputs with the same inputs. So precise traffic control cannot be guaranteed. So that leaves us to the final solution, which is that let's modify the mapping stage. And
thank you. So I'll continue from here. Okay, I'll dive into the details of our design, where we will try to modify the mapping stage. First of all, let's look at how ECMP's mapping stage work. So there are essentially two values to determine the output port. The first is a group selector. Normally, we use destination IP address as the selector, and it will point to a base ECMP group, which is group 0 in this case. Then we also have this 5 tuple. It will go through the hashing process, and then the outcome from the hashing process is a number. It will range from 0 to n-1, and let's assume that there are total n next hops. And in this case, the output is n-2, so the final output port will be n-2. Okay, so one solution is let's modify the ECMP to change the outcome from the hashing process. Basically, we will try to redirect the item selection in ECMP group. Nevertheless, this will have some compatibility issues because not all the switches support such function. And this conflicts with our goal of deploying today. Instead, our solution is to redirect the ECMP group. So essentially, we propose to use additional field as the group selector. This can be any field, but in this case, we use IP DSCP field. By default, the selector points to group 0. And then we'll create additional ECMP groups, each containing items in different order. And now, let's say we change the selector to a different value. For example, let's let s equal to 2 in this case. Then the selected output port will be different. Right. In this case, it becomes n-4 instead of n-2, as in group 0. So this is an interesting feature that we can leverage. To systematically explore this feature, we propose 2 programming models, each with different use cases. So in the first model, we construct the forwarding table in this way. So for group 1, we shift all the items in group 0 to the left or to the right. In this case, it's to the right by 1 item. And for group 2, we shift based on group 1, and so on, and until group n-1. And we iterate all the possibilities. So in this way, we enable precise traffic control of path offset. Basically, it means that we will deterministically deviate the selected next hop or path. Basically, with a given selector S, it will always deviate the packet or flow to S minus S0 next hop or path. Okay, so this model actually enables a range of use cases where randomness still plays a role, such as network failover. Basically, the host doesn't know what path is the flow traversing through, but it knows that sometimes, in case of failure or congestion, we will need to deterministically avoid a failed path. And by doing that, to do that, we only need to embed a non-zero selector. And another example is load balancing, and there are also multipath protocols and so on. Okay, so in the second programming model, we construct the table differently, as shown in this figure. So basically, all the items of each ECMP group is the same. And in this way, we can use selector to control which exact next hop or path that we hope to choose. This enables very precise traffic control. And this also enables another set of use cases that demand explicitly control of the network path. For example, when we have network failure localization, we hope to traverse all the path using the minimum set of packets. So we need to set a path for each of them. And also, we sometimes it also applies to packet spring scenarios and segment routing and more. So note that these two models, they can coexist. So we just need to concatenate the ECMP groups, which forms a larger forwarding table. Okay. So to translate the program model to actual deployment, we have built a compiler. It takes several inputs. First is the topology, usually as a adjacency matrix. And after that, the desired precise traffic control type is either a path offset, or exact next hop, or both combined. And finally, we also need to consider constraints such as SRAM size, and then our compiler will generate forwarding table plan for every switch in the network, and we will put this configuration to the switches in network. And during the forwarding table update, inconsistent may happen. So note that here, when we talk about update, it's only needed for permanent changes, such as when we add or remove a part of the network. And for stationary changes, such as temporal switch or link failure, update is not needed. And keeping the consistent is hard because we need to update all the end servers, so that would change the way of how they select the selector. Also, there will be always packets in flight, and we need to consider that. To solve this problem, we propose a transactional update mechanism. Basically, we will divide the ECMP to two sections. We label the forwarding table with different versions. For version 0, we put it in the upper section. And when an update is needed, we then put the version 1 at lower selection. Meanwhile, the version 0 is still available for a short while. So it is fine if we didn't update all the end servers in time, and they can still use the table for a small time. And similarly, when version 2 is available, we just replace version 0 with it, and so on. So in this way, ensure the consistent during forwarding table update. Now let's move on to evaluation. So first, I want to show that about ECMP group consumption. As I mentioned, our solution basically adds more ECMP groups. So here, the axis represents different topology. More details are in the paper, but each topology have different sizes, and topology 12 is the same as our production network. And y-axis is the number of ECMP groups needed to enable PECMP. And we can see that the maximum number of ECMP group is actually 128. But actually, switches today have over 8,000 ECMP groups. So PECMP only consumes less than 1.5% of total space, which is totally acceptable. This is not a concern at all. Okay, so next, let's look at specific scenarios. Network failover, as Congcong mentioned. So to evaluate, we compare against PRR, which was proposed in 2023 by Google for protective reroute. They use TCP/RTO as the indicator for network failover, and once failure is detected, they will try to repath the flows by changing the port number. So basically, they will try to repath the flow randomly. And this figure shows the city of failure recovery time. The orange, green, and yellow lines represents PRR with different failure location at top of rack, leaf, or spine switches. The result is different because each failure localization has different number of available next hops. But overall, multiple attempts is needed to perfectly repath all the flows. Instead, PECMP is in the blue line, which is hard to see, but basically it will always succeed in the first attempts in repathing. So by that, PECMP outperforms PRR in terms of reliability and failure recovery time. Okay, another use case is load balancing. In 2002, again, Google proposed PLB, which repath flow upon detecting congestion. Again, the repathing is random. So to index validation, we use the same topology as the production network, and we adopt the same congestion detection signal with PLB. And this is some of the results. This table shows the normalized tail latency, tail flow completion time on the different network load. Okay. We can see that PCMP outperforms PLB. And we have more evaluation in different scenarios. Please refer to our paper for more details. And finally, I would like to mention that PNSME has been deployed in Tencent Cloud to support a fast network failover. Again, this figure shows city of service downtime before and after deploying PCMP. And we can see that PCMP effectively reduces the service downtime. Okay, so in conclusion, randomness and precise traffic control are both important in today's data center networking, and we propose programmable ECMP that leverages extra ECMP group to realize precise traffic control. And PCMP enables many critical scenarios such as network failover and load balancing and more. And finally, it has been deployed in production network. That wraps up the talk, and happy to take any questions. Thank you.